type of crystallizer under the cooling crystallizers, and we call them DCCs, or the direct contact cooling crystallizers. Now, in DCC, supersaturation is achieved by allowing the processed liquor to come into contact with the cold heat transfer medium. Now, advantages of this DCC include better heat transfer and lower cooling loads. Although disadvantages include product contamination from the coolant because there's direct contact of the coolant with the product, and the cost of extra processing required to recover the coolant for further use. Now, crystallization processes employing DCC have been used successfully in the dewaxing of lubricating oils, desalination of water, and the production of inorganic salts from aqueous solution. Now, the second group of crystallizers, so we have finished with the first one, the cooling crystallizers, are the evaporating crystallizers. So in here, we expect a certain amount of the solvent present in the carrier solvent that is present in our original feed to be evaporated so as to concentrate it. Now, if the solubility of a solute in a solvent is not appreciably decreased by lowering the temperature, the appropriate degree of solution supersaturation can be achieved by evaporating some of the solvent using the oldest and the simplest technique, and that is the use of the solar energy. Now, common salt is produced widely from brine in steam-heated evaporators, multiple effect evaporator crystallizers, and these are used in sugar refining as well, and many types of forced circulation evaporating crystallizers in large-scale use. Evaporating crystallizers are usually operated under reduced pressure evaporating crystallizers to aid solvent removal, minimize heat consumption, or decrease the operating temperature of the solution. So we want to decrease the operating temperature. As such, we operate it under reduced pressure. Now, we also have, so this is the third type, the vacuum adiabatic cooling crystallizers. Adiabatic cooling, that is. So a vacuum crystallizer operates on a slightly different principle from the reduced pressure discussed in the previous slide. Since supersaturation here is achieved by simultaneous evaporation and adiabatic cooling of the feedstock. So in the first one, we concentrate the solution by removing some of the solvent, the carrier solvent. In here, not only do we remove some of the solvent, but at the same time, we cool it adiabatically. So a hot saturated solution is fed into an insulated vessel maintained under reduced pressure. If the feed liquor temperature is higher than the boiling point of the solution under the low pressure existing in the vessel, the liquor cools adiabatically to this temperature, and the sensible heat and any heat of crystallization liberated by the solution evaporates the solvent and concentrates the solution in the process. So in the third type here, we have adiabatic, so there's no amount of heat that is liberated from the system. It is the crystallization process is operated under vacuum, so as you are able to reduce the amount of solvent present in the feed, at the same time cool it simultaneously or together with the lowering of the solvent content. Now, the last type are the continuous crystallizers, and these are usually the crystallizers that are coming out of the board exam, aside from the Swenson-Walker type of crystallizer, which I have discussed. Now, under the forced circulation crystallizer, we have the Swenson forced circulation crystallizer. So this is a modified version of the standard Swenson-Walker crystallizer. This is operating at reduced pressure and has a high recirculation rate through the use of an external heat exchanger, which provides good heat transfer with minimal incrustation. meaning your crystallizer sides or the sides of your equipment are not encrusted with crystals. Now, the fluidized rather bed crystallizers, as an example, we have here an Oslo fluidized bed crystallizer. So a bed of crystals is suspended in the vessel by the upward flow of the supersaturated liquor in the annular region surrounding a central downcomer. Although originally designed as a classifying crystallizer, fluidized bed Oslo units are frequently operated in a mixed suspension mode to improve productivity, although this reduces the size of the crystal. So take note of this. Your fluidized bed Oslo units are operating on mixed suspension mode, which is actually the last sample problem that we'll be discussing. So in here, your bed of crystals remains suspended by the upward flow of the supersaturated liquor in an annular region surrounding a downcomer, a central downcomer. So there is some sort of an opening in the crystallizer unit, and your supersaturated liquor is remaining suspended in the annular region surrounding this central downcomer. And your unit is in the mode of mix, is in like mixed suspension type of mode, meaning a certain amount of the grown crystals, that is, remain suspended in the solution while a new one is being processed. So that is why it's called mixed suspension mode. Now we have under here also the draught tube agitated vacuum crystallizers. So in a Swenson, so again, another Swenson modification, draught tube baffled vacuum unit, a relatively slow speed propeller agitator is located in the draught tube that extends to a small distance below the liquid level. Now, hot concentrated feedstock enters at the base of the draught tube, and the steady movement of magma and feedstock to the surface of the liquor produces a gentle, uniform boiling action over the whole cross-sectional area of the crystallizer. For this crystallizer, the degree of supercooling produced is less than 1 degree Kelvin, and in the absence of violent vapor flushing, both excessive nucleation and salt buildup on the inner walls are minimized. The eternal baffle forms an annular space free of agitation and provides a settling zone for regulating the magma density and controlling the removal of excess nuclei. An integral elutriating leg may be installed below the crystallizing zone to effect some degree of product classification. So in the case of this DTB, modification of the Swenson draught tube, you have some form of an agitator that extends well below the liquor level. So the purpose is, of course, your magma to be well agitated at all times, minimizing the excessive growth of new nuclei. The purpose is for the old nuclei to grow to a certain size that it is ready to be withdrawn from your crystallizer and new ones being processed. But this is also, processing the feed in mixed suspension type, just like the previous one, the letter B. Now, and speaking of the mixed suspension, so this is the MSMPR type of crystallizer, mixed suspension, mixed product removal. Mixed suspension, mixed product removal type of crystallizer. And this particular formula is applicable to the last group of crystallizers I've just discussed. It's because a certain amount of the old magma that has growth to a certain size is kept within a pool inside your crystallizer unit while a new one is being processed. Now, the formula that you are seeing here is a formula that determines the magma density, which is a measure of the solid content, and it's represented here as C sub S. And you have alpha as the volumetric shape factor, the crystal density as our rho, and the N naught, the nucleation rate, the G sub D, the growth rate, and the T sub R in crystallization is referred to as the drawdown time. It's the time wherein your magma is ready to be released because the size of the crystals that are formed are already within the specifications or the objective of the whole crystallization process. But in other equipments, it's just the simple time we call the residence time. The time that your feed to be processed is staying inside your equipment, or the time it stayed inside your equipment for it to be able to grow to a certain size. Now, it's just given a different name here, which is a drawdown time, or simply the residence time. Another formula that we will be using in this fourth group of crystallizer is the N prime, which is also dependent on the GD and the drawdown time. So you have here now the crystal size, the diameter that is. Then you have the N naught, the population density of the nuclei, and the rest are also the same as the formula that you are seeing in the previous slide. So this is your number of crystals per unit size per unit volume of the system. The number of crystals produced per unit size per unit volume of the system is a function of all this. Again, empirical in nature. So we have this last sample problem for an MSMPR crystallizer, which is operating with a steady nucleation rate of N naught equal to 10 raised to 13 per cube per meter raised to 4, a growth rate G sub D equal to 10 raised to negative 8 meters per second, and a mixed product removal rate based on clear liquor of 0.00017 cubic meter per second. The volume of the vessel based on clear liquor is 4 cubic meter, and the crystal density is 2,660 kilogram per cubic meter, with the volumetric shape factor being equal to 0.7. So we are to determine all this: the solids content in the crystallizer, the crystal production rate, the percent nuclear removed and the discharge by the time they have grown to 100 micrometer. And last is the liquor flow rate, which passes through a trap which removes 90% of the original nuclei by the time they have grown to 100 micrometer. Juliana, close the door properly. So what we're going to do here, sorry class, is to start writing what the problem requires us, and then start our solution by the formula that we will utilize in determining what the problem requires. So let me stop sharing here, and I'll go to the board. Wait, class. Okay, so I have read already the problem, so I will write down the given information provided in the problem here. I will just go back to the slide from time to time. That way we can pick out the information that we have based on the problem that I have read. So I will read the problem state per statement. So you're given an MSMPR crystallizer operating at a steady nucleation rate, a growth rate, and a mixed product removal rate based on clean liquor. So all three informations were stated. So I'd like to write these three information now in our board. So your nucleation rate is given to be 10 raised to 13 per meter to the fourth. Then we have the growth rate, which is 10 raised to negative 8 meters per second. And we have product removal rate equal to 0.00017 cubic meter per second. So this is based on clear liquor. Okay, that's the given information on the first statement I've read. So the nucleation rate is 10 raised to 13 per meter raised to the fourth. The growth rate is 10 raised to negative 8 meters per second. And the mixed product removal rate based on clear liquor to be 0.00017 cubic meter per second. The next statement says that the volume of the vessel based on clear liquor is 4 cubic meter and the crystal density is 2,660 kilogram per cubic meter and a volumetric shape factor of 0.7. So another 3 information for this. So we're given the volume, which is 4 cubic meter, again based on clear liquor. And we're given the density, 2,660 kilogram per cubic meter. And the last, which is the volumetric shape factor, which is 0.7. Hi. Now, 6 information given by the problem. Then we go to the required information. So you are asked for letter A, the solid content of the crystallizer. So we have read it a while ago. The solid content or the magma density is represented by C sub S. And letter B, we have the crystal production rate. So we have crystal production rate. And then we have, this is crucial, this one. The percent of nuclei removed in the discharge by the time they have grown to 100 micrometer. Percent nuclei removed. So size is greater or equal to 100 micrometers. So they will only be removed if their size is greater or equal to 100 micrometers, meaning this is the size requirement. If they have not grown to this size, they won't still be removed. And then letter D, the liquor flow rate, which passes through a trap, which removes 90% of the original nuclei by the time they have grown to 100 micrometer. So then the liquor flow rate, which passes through a trap which removes 90% of the nuclei by the time they have grown to 100 micrometer. So this would be the, I'd like to write it as liquor flow rate. So the liquor flow rate, we represent our liquor as L. So the liquor flow rate when 90% is removed. When size again is greater or equal to 100 micrometer. So the liquor flow rate, which passes to a trap, which removes 90% of the, shall I say, the mixed suspension already when their size already reach 100 micrometers. So these are the three, or rather the four unknowns of the problem. So we'll start with the first one. And since I have written it already in terms of its representation, the C sub S, this is actually a measure of the solid content. So when we are asked for the solid content of the crystallizer, we are actually determining the C sub S. And a while ago, I have shown to you the formula for this, and I will write the formula here. So our formula for this one is 6 alpha rho and not, and then we have G sub D times the drawdown time, or the residence time raised to 4. So if this is our formula, we will check what we have and what we still do not have. So let's see. This alpha is the, as defined, it is the, excuse me, volumetric shape factor, the one I have wrote as a volumetric shape factor here. So I will write this one as alpha, the volumetric shape factor. So I have already the alpha, the first one I see. The rho is the density, so it's already given. The next is the N naught, the nucleation rate. It's also given. So I'm checking one by one the things that I need for this problem. The G sub D is also given. So then we have the last is the drawdown time. So if you look at what is provided for us, we don't have the drawdown time. We only have the nucleation rate, the growth rate, the product removal, the volume, the density, and the volumetric shape factor. So for us to be able to determine the solid content, and that is the C sub S, we need to determine the drawdown time. So your drawdown time, of course, should be able, or should be easily determined based on what you are provided here, or you are to look for a way to find the time based on what's provided in here, in the given. So in the given, we have the product removal rate, and this is your volume. So if you're going to look intently on the two bidimensional analysis, if I divide the volume by the product removal rate, that would give me the drawdown time, or the time that I will remove already the magma inside my crystallizer, because they have already reached the size which I want them to, of course, become. So in this case, we will have your 4 cubic meter. We divide that by the 0.00017 cubic meter per second. Okay, so this will give us a drawdown time, or a residence time, of 23,530 seconds. And now everything was just a matter of substitution to the formula. Okay, so if we will substitute to the formula, the values, we have 6, our volumetric shape factor of 0.7, our density, which is 2,660, our nucleation rate of 10 raised to 13, our growth rate, which is 10 raised to negative 8, and we need to multiply this to 23,530. And by the way, our time in the drawdown time should be in seconds. Okay? Everything else has conformed to the unit that we want for our solid content. And that's the density of the magma itself. So in this case, we have now how much? 342.47 kilogram per cubic meter for our solid content, which is what I have said already, our magma density. This tells you how much of a solid is contained in the magma itself. So the solid content. Now, next requirement is the production rate. So we'll go to the next sheet. You will find for the production rate. So our production rate, again, will be based on the magma itself, because our crystal production is dependent on the solid content of our magma, then we will get it from here. If our production rate should be in mass per unit time, and this one is density, kilogram per cubic meter, then we will use the given of the production rate in cubic meter per second to get a production rate in mass per unit time. So our production rate here, just like any production rate, when we speak of in chemical engineering or in production, that's having a unit of uh, mass per unit time. And since, as I've said, the crystals that we are producing is dependent on the solid content of our magma, then I'll be using the amount we have taken here. We have solved in the previous, which is 342.47 kilogram per cubic meter. We will multiply it with the production rate, cubic meter per second. Actually, it's defined here as the product removal rate. Your product removal rate is still your production rate. So in this case, you will have now a production rate which is in mass per unit time. Okay? Using the principle that your crystals will be coming from the magma, because your crystal is just a separation of your liquor coming from the magma, and you have already the crystal. So in this case, you have 0.0582 kilograms per second. So in terms, that's very small because it's per second. But if we will change this to hours, we will multiply this to 3,600, then it would not be as small because this is per second. So per hour, our production rate is 209.59 kilos per hour. So not bad. 209.59 kilograms per hour of crystals. Now we go to letter C. So if we will be disconnected, just use the same link. In letter C, you are asked to determine, go back to what is being asked here. The percent nuclei removed by the time they have reached 100 micrometer. So let's go back to the formula that so far we can only use in the case of MSMPR. And that formula is N equal to, let me check on our PowerPoint. Okay, we have N prime equal to N naught, then the exponential factor, so it's N prime. So I'll go back to that. So this would be N prime equal to N naught, then this whole exponential factor, exponential function, then we have EXP. Then we have negative, I forgot again the formula. D, negative D, GD over R. So you have negative D, then you have the G sub D, T sub R. This is our formula for the N prime. Again, what is that N prime? And this N naught in the first place. So N prime is the number of crystals per unit size per unit volume of the system. Number of crystals. The N naught is the population density of the nuclei. Number of crystals, iniya, number of nuclei. The nuclei still has to grow for it to be considered as the crystal. So let's see. We expect that our nuclei, number of nuclei, will be bigger in number than our number of crystals per unit size per unit volume. Let us go back here. So it says in the problem that we are asked to determine the percentage of the nuclei that have been discharged by the time they have reached 100 micrometer. The number that had been discharged. So what we can do here is get the number accounted for. So I'd like to get the percentage of the amount of nuclei originally present that has turned into crystals that is accounted for. This one we can account. So we have N prime over N naught. Then we have exp here, negative. Our diameter is 100 micrometers. So this is 100 times 10 raised to negative 6. And that's in meters already. Then we divide this by the G sub D, which is 10 raised to negative 8. And the T sub R we're going to use here is the T sub R we got a while ago, 23,530. So this would be the 23,530. So now you will have an N prime over N naught, the accounted for crystals remaining in the system being equal to 0.66. And since the problem is asking how much was already, I'd like to go straight to that original question so you will understand. It says here, the percent of the nuclei removed in the discharge by the time they have grown to 100 micrometer. The one that you have already removed are the ones that you were not able to account. So in this case, this number is still accounted for, because it's based on the diameter of the crystal, the growth rate, and the residence time. This is the one remaining inside the crystallizer. So the one that was removed, so removed percentage is equal to 1 minus 0.66. This you were able to account. So meaning the one that you were not able to account is the one that were removed already, because they have already grown to the size of 100 micrometer. So this formula accounts for what is inside the crystallizer. Now, the one that you're not able to account is the one that was removed already. So that is in letter C, based on the original question of the percent of nuclei removed in the discharge by the time they have grown to 100 micrometers. So they were removed already because they have reached the size requirement. Okay, so the last question is, I'll read the question. The liquor flow rate which passes through a trap which removes 90% of the original nuclei by the time they have grown to 100 micrometer.
90% was already removed or is to be removed by the time they have reached 100 micrometer in size, then only the 10% of the nuclear remaining has to grow to 100 micrometer. And this 10% will be your N prime and N naught, which should be substituted to this particular equation here. So the formula for N prime divided by N naught is actually equal to exp, or an exponential function, with the argument negative d over the g sub d over also the t sub r. So the size of the nuclei, the growth rate, and the drawdown time. Okay. In here, from this particular value of 10%, that's the remaining nuclei. The 90% cannot be accounted anymore because they are to be withdrawn because they have grown to that size of 100 micrometer or more. Now, this remaining 10% will stay in your MSMPR for 4,343 seconds. So this is the residence time, or this is the drawdown time of this remaining 10% inside the MSPR. Now, if this is the drawdown time or the residence time, then that could be equated to the volume of the crystallizer, the MSMPR, and the sum of the liquor flow rate and the mixed product removal rate. So remember that in the case of the MSMPR, you have a mixed suspension at all times inside your crystallizer. So the mixed suspension consists of the grown crystals, or the remaining crystals that need to be grown, plus the constant flow rate of the clear liquor to your crystallizer. So it has to be the, shall I say, the mix of the grown crystals plus the pure liquor flow rate. So the volume divided by this volumetric flow rate of the mixed product and the clear liquor will be giving you this time, which is 4,443. In this case, if we substitute the values to our formula, so you have 4 for the volume of the crystallizer, and you have 0.0017 in cubic meter per second for the product removal, then this would be the clear liquor flow rate. So the reason why you have to add the mixed product removal rate and the liquor flow rate, it's because at any time inside your crystallizer, you have these two being processed. Now, inside your crystallizer is a suspension consisting of the mixed product that is continuously removed and that of the clear liquor that is continuously also fed into your crystallizer. So that is why in here in your denominator, you have the sum of the two. So this will give you this value of the clear liquor flow rate. So you have 0.0075 cubic meter per second. This would be quite small considering that this rate is per second. But if you convert this to hours, so it's more or less acceptable now with 2.68 cubic meter per hour as the clear liquor flow rate that is processed by your crystallizer together with the remaining suspension of the crystals that need to grow, because we only dispense the 90% that has grown to that particular size of 100 micrometer or more, meaning the remaining 10%. There is always a remaining 10% inside your crystallizer. So this now ends the fifth sample problem, our last sample problem under industrial crystallization. Okay.